first start off with a brief video, a few minutes, watching the Intel Ocotillo Technology Fab video. Enjoy watching this video, and then we will get started. We'll be back to you soon. Okay, well, hello everyone. Welcome to the virtual Fab Tour. Intel alumni, Intel retirees, and current employees, we are all among friends attending today's event. My name is James Cape, and I am the current president of the Intel Alumni Network, and I was at Intel from 1983 to 2001. We are delighted today to have esteemed Intel alum Dr. Paolo Gargini in conversation with Jim Evers and Michael Fendrick from the Intel Arizona Ocotillo campus. And with that, let me hand it over to Paolo.
Thank you, James, and good day to everybody. Thank you for coming to this Intel alumni event. It's all in the family, so please let's talk frankly about what we want to say, and we cannot say in an open forum. But first of all, let me introduce the esteemed panelists. First of all, Jim Evers. Jim Evers has been an Arizonian all together. He likes the number 2. He worked in number Fab 12, Fab 22, Fab 32, Fab 42, and now you can see Fab 52 and 62, but only for a short time, because actually we will be a donation because it's going to Ohio. So we'll have donation. If you have sweaters, underwear, very warm one, anything, he'll have a shock. So please be nice to him. Anyway, he's essentially managing the most advanced Fab 42, and he has accepted very kindly to go to Ohio on our behalf and on behalf of the Social Security checks and the Medicare that I get. Thank you very much, Jim, for your operation. Let me also introduce Michael Fendrick. He's the manufacturing system group manager. So he takes care of everything that Jim cannot get to. So he covers all the elements, recruiting, training, equipment, whatever you have to do. Both of them have been for 30 years plus with Intel. So I have been with Intel for 34 years, as some of you know. And so I think with this, it's best to initiate because we have a lot of cover. I look at the videos, they are exceptional. If any of you have been in a fab before 2003, you'll be shocked. And for those of you that have never been in a fab, you'll be even more shocked. So with this, I would like to turn into Jim, and they can introduce the first video. Jim, please.
Yeah, great. Hey, it's wonderful to be with you today, all my Intel alumni. Can I do a plug though, which is if any of you are bored out there and thinking maybe you want something to do, we're going to be staffing up Arizona, staffing up Ohio. There's some options for you, okay? But when I was asked to show you a little bit about IDM 2.0 in our factories, I thought to myself, well, do you want to hear somebody talk or do you want to see something cool? And so we thought it'd be best to show you something cool. So we have a series of videos here. This first video then is the sand to silicon, because I know at Intel, we've all been at different parts. Some of you have been in the fab, some of you haven't been in the fab. So it gives you a good sand to silicon introduction. So let's roll that video first.
The world is producing data at an unprecedented rate, faster than our ability to analyze and understand it. To move, store, and compute all of this data requires incredible processing power. From the blazing speeds of our devices to blazing trails within AI, Intel builds chips that are at the heart of nearly everything. Within every Intel chip manufacturing facility across the globe, innovators are pushing the limits of science and literally rearranging atoms to create groundbreaking technology. This strong silicon foundation is what gives each Intel chip limitless potential. At the heart of all modern electronics, the transistor is a tiny switch, 10,000 times smaller than a human hair, that controls the flow of electrons through a circuit. To build a processor, billions of transistors are packed into an area no larger than a fingernail. It's one of mankind's most complex feats, and a remarkable achievement that Intel has essentially doubled transistor density in every new generation of processors. The process begins when silicon-rich sand is melted and cooled, forming a solid, which is then sliced into wafers. Once inside an Intel fab, the raw wafers begin their long journey through an incredibly complex process. They're loaded into front-opening unified pods, or FOUPs, which travel hundreds of miles along Intel's automated superhighway, going from tool to tool, as processors are painstakingly built up on each wafer. The wafer first goes through a series of important steps, such as photolithography, ion implantation, and etching, that prepare it for the critical transistor formation process. Intel was the first to manufacture three-dimensional transistors called FinFETs. FinFET construction requires first building a channel in the form of a fin. Intel has devised several innovations to overcome fundamental barriers to continued transistor scaling. One such innovation is a breakthrough fabrication method called gate last. It involves building, then removing a temporary gate in order to precisely place the dielectric material and metal gate. This allows for the gate to wrap around the fin and control the flow of electrons through the channel. Another invention moves the transistor contact directly over the active gate. To accomplish this, the gate material is recessed and then filled with insulating dielectric material to prevent the creation of a short circuit. Next, the dielectric near the gate is etched, filled with metal, recessed, and capped to allow a novel self-aligning process that enables the high-density contact geometries. Now, the dielectrics are etched selectively to expose only the desired part to connect to the first metal lines. This is done through an innovative via etch and deposition scheme, allowing contact over active gate to happen. Finally, dozens of layers of metal interconnect lines are added to complete the circuit. After more than 1,000 of these complex steps, the wafers are finally prepared for singulation and packaging. Innovative processor packaging has become a critical feature of advanced computing architecture. 2D and 3D packaging technologies are enabling new device form factors and additional boosts in performance and energy efficiency. Testing of the final product ensures that every chip exceeds our performance and quality standards. In addition to adding more performance and features with each new processor generation, Intel's integrated design and manufacturing capabilities have enabled humanity to innovate game-changing technologies that impact nearly every facet of modern life. Intel keeps powering the world. At the same time, we're powered by you, the makers, the dreamers, the doers, the people who share in our history of making the world smarter, faster, and more connected.
All right, that was the first video. You know, and we have Paolo here, who's an industry expert. You want to, I don't know if you want to say anything about the video there.
Well, I simply wanted to say, I don't know if you've seen some of the advertisement on Amazon. They have a warehouse where they can move a box from left to right. And I laugh whenever I see it, and they call it automation, right? So as compared to what is being done daily in one of Intel fabs. This is still a long way to go. So I think especially for the alumni that hadn't been in a fab, maybe some of them ever, and the guy in sales, they never know what they were really selling. So now you have an idea, how all of this is done. So that was my reaction. And Jim, do you want to add something?
Yeah, no, I think it's a privilege every day that we get to work with, the material science folks that are able to take processes and turn that, sand into silicon, which becomes products for our customers. We definitely continue for the time that you were here. We still are customer obsessed and making sure that the products go out and are competitive in the market. So that's the first video. The second video we have for you then is a little bit of a repeat around the transistors, but it gives it a bigger flavor around the factory itself. So if we could, why don't we show that second video?
Making a computer chip requires the most complex manufacturing process humans have ever devised. For more than 50 years, Intel engineers and scientists have continually faced, then overcome, the challenges posed by physics when the features on a chip shrink to the size of atoms. They've developed new ways to squeeze billions of microscopic switches, called transistors, onto ever smaller computer chips, many as small as a fingernail. Transistors 10,000 times smaller than a human hair that cycle up to 5 billion times per second. Back in 1965, Moore's Law, named for Intel's co-founder Gordon Moore, predicted that the number of transistors on a chip would roughly double every 2 years. Intel R&D engineers, mostly based in Oregon and Arizona, have followed the Moore's Law metronome year after year, with inventions such as high-K metal gate technology, tri-gate 3D transistors, and strained silicon. These advances have paved the way forward for the entire industry. They are the foundation to enabling modern technology's infrastructure, including the internet, mobile computing, cloud computing, and artificial intelligence. And it's not just about silicon innovations. Intel's more recent advanced packaging inventions, such as EMIB and Foveros, allow us to interconnect together multiple chips on a single tiny package. Our focus on R&D, we invest billions of dollars every year, has been the foundation of our success and industry leadership. Once chip architects create the highly complex blueprint for new computer chips, they're sent to one of these massive semiconductor factories, or fabs, for manufacturing. Building a new fab fully equipped costs about $10 billion and takes 6,000 construction workers about 3 years. A finished fab generates about 10,000 jobs, 1/3 of them in high tech. A typical Intel fab requires 35,000 tons of structural steel, more than 5 times the weight of the Eiffel Tower. The clean rooms in a typical sprawling factory cover the equivalent of 4 U.S. football fields. It often takes 2 semi-trucks to deliver each of the fab's 1,200 multi-million-dollar tools. Some of these tools weigh as much as 5 tons, the weight of 3 mid-sized cars. Most Intel fabs include water reclamation facilities. 90% of Intel's water use is restored or returned to the environment. By 2030, Intel aims to reach net positive water, putting more water back into the environment than we use. Once a fab is up and running, this 27-mile automated material handling system shuttles blank silicon disks to hundreds of tools that eventually turn them into wafers, containing hundreds of Intel chips. Intel manufacturing and packaging is operating at a mega scale worldwide, requiring a global supply chain that stretches across multiple continents. Once they leave the fab, computer chips are shipped to Intel's assembly and test factories, where they are put into protected packages and tested. Our assembly and test factories send our packaged chips to one of our 17 distribution hubs across the globe. Intel teams there ship almost 2 billion units a year to over 2,000 customers. Our vast supply chain includes 8,000 products and 16,000 suppliers in 100 countries. As the chip-making business grows ever more complex, Intel is one of the few remaining firms in the world, and the only one in the US, that does it in-house. Design, manufacture, ship, and sell.
Oh, what do you think there?
I had a few comments. When I was in Fab 3, it was 10,000 square feet. And then we built the manufacturing fabs, Fab 4 and Fab 5. They were 24,000 square feet. And then we went from broke, in Phoenix and Albuquerque, we crossed the 30,000. But then we were really smart. Fab 9.1 was going to be 100,000 square foot, and we're going to be 4 factories progressively, allocated there. Of course, it never happened because we kept on eating our space and more until half of the building was used for Fab 9.1. And so now you have a 200,000 square foot fab, and that's a typical size nowadays if you want to have enough wafer starts. So 4 football fields right now. The other thing that's interesting, assembly used to be a remote site. We would send Michael to Vietnam, told those guys to put some stitches here and there. And now the complexity of assembly is comparable in many ways to making really integrated circuits. Fortunately, we have a lot of automation to place all these die one next to each other. And this technique we began in 1992 as an exercise where we began doing bumps and trying this. And I went to marketing and they said, no, come back in 20 years, it's too soon, okay? So I'm glad that eventually he came, okay?
Yeah, that's great. You talked about the size of the fabs. I'll share a little bit because we'll show you Ocotillo here in a minute. Our 4 fab network here is about 1 million square feet of clean room space, about 17 football fields that we have. And then when we add 52 and 62, it's about another 10 football fields. So they're not small fabs that we're going to be adding here.
So 200,000 was the starting, right?
Yeah, so it's a big fab. Yeah, 200,000 each approximately, right? So.
Yes.
And I think the amazing part is now that we've connected them all too. If you were to walk from Fab 12, you can connect all the way without going outside. It's about a mile walk to go from Fab 12 to go all the way to Fab 42. Get your steps in.
I wanted to ask you, did you connect the automation so that you can shuffle wafers among the fabs? So you have the 4 fabs connected?
Yeah, Mike, you want to? What do we call those links? We have a fancy name for it.
It's the ASH, or the automated superhighway.
Yeah, the superhighway. Yes. So that was another idea, that we could move. First of all, I imagine that you're still dividing the fab in 4 blocks for insurance or something, firewall. I don't know how you handle that, but in any case, to go from one fab to the other, it was very painful. So one of the ideas that sometime in the future we can automate the transfer, and you say you've automated the 4 factories. I look at the picture, I can see there is a corridor that connecting them, and I hope there would be on the ceiling, 1 or 2 rails that are connecting, the automation to the different fabs. So, yep. And then you still have to add 52 and 62 next, right?
That's right. That's right. And so one of the things to get an advantage for scale, by connecting them all, we can operate as a single fab network. So it's gives us that super mega site feeling with all of those.
Hey, Jim, another thing, right? I remember, the Israeli wanted the number 8 for the fabs because it means something good for, and then number 2 was really Arizona. Then 7, 9 was New Mexico. What is it going to be the number for Ohio?
Great question. Lucky 7. So
Lucky
my first
7.
fab in Ohio will be Fab 27. So we'll start with 27
okay.
because once upon a time we had a fab in Massachusetts, which was called Fab 17. Yeah. So,
but I was considering between 3 and 7, right? But 13 may come out. That is the unlucky number, right? So I bet on 7. So thank you for making me win my bet.
Yes. Oh, very good.
Okay, go ahead, James. You have something else to show us.
So I have a third video for you, but I'll set this one up a little bit because I'll say that even as recently as 2 years ago, we didn't do any fab tours. We really wanted everything to be, not exposed, not quiet. But what happened when Pat joined and rejoined Intel again, and he came up with a strategy for IDM, Integrated Device Manufacturer 2.0, and wanted to go big on, doubling down, getting us into the foundry space with Intel Foundry Services. And he was out here last March announcing Fab 5262, okay? And since then, it's been, overwhelming how much we are trying to get out there and tell the story of how important it is for us to bring domestic manufacturing in from a supply chain standpoint. And we're too concentrated in Asia. We want to spread that out to United States and to America. And so what that, then we started to put these, videos together, overviews for, our politicians to help influence them on things like CHIPS Act, et cetera, and tell our story. And so today it's very special because we, super secretive, can't be in the fab, but I'm going to give you an inside look. You see some of the videos of my fabs today in Ocotillo and a couple other things that are really important for the fab operation. So this next set is something that, the first couple you could probably find out on YouTube. This next set is a special treat just for you.
Hello, my Intel alumni friends. My name is Jim Evers, and I'm standing here in the middle of Fab 42, the latest active operational fab in the 4-fab network of Ocotillo Technology Fabrication here in Chandler, Arizona. It's the largest fab network in all of Intel. And if that wasn't big enough, last year Pat announced 2 new fabs, Fab 52 and Fab 62, to continue to grow. And so we thought it would be a really good treat for you to be able to look inside these fabs and its operations and see what our water reclamation facilities look like, what lithography looks like inside the fab, and what our remote operations center that runs all of this fab network looks like. So I hope you enjoy this treat, and you can see how we're gonna win IDM 2.0. At Intel, it's not just about the operations and the chips that we make, it's also about how we make them. And Intel's RISE strategy of being responsible, inclusive, sustainable, and enabling is a big part of that. I'm out here in front of Ocotillo's water reclamation facility with Aaron. Aaron, how you doing?
I'm doing great, Jim.
What's the big deal with water?
Everything's big about water, Jim. Behind us is our brand new water treatment plant that, in conjunction with the brine reduction facility that we built from the beginning, allows us to treat 12 million gallons of water a day that we can then take back and recycle for reuse at our plant or deliver to the city for their use at better than drinking water quality.
Wow, it sounds like we use a lot of water here, water in the middle of deserts.
We do. About 80% of the water we use is to make ultra pure water. To make that, a lot of the water the city gives us has to come here, where again, we can treat it, allow it to recycle, or allow the city to use it as a high quality water source.
You mentioned the city. It sounds like we're working closely with local governments.
Yeah, since 1995, when the Ocotillo campus started, Intel funded and pays to operate the brine reduction facility that the city runs. Again, we just built this facility, which we'll run. Together, those are coordinated to produce that 12 million gallons a day of recycled water that we both can use through a coordinated effort.
That's brilliant. Anything else?
100% of this is powered by green power.
That's a beautiful, sustainable plan. Thank you, Aaron.
Thank you.
You can't talk about the fabs without talking about lithography. And I'm here with Kevin, one of our litho area managers. Good morning, Kevin.
How you doing, Jim?
So when they talk about process nodes, it refers to lithography. Tell us how that works.
Lithography, I would say, is the heartbeat of the factory. It's one of the most critical process within the manufacturing flow. If you think photography, lithography is the same process on a much smaller scale. It involves taking light that passes through a series of mirrors or lenses and focuses a pattern on a mask or reticle down onto the wafer in a really minuscule fashion. That helps us print the transistors, and we have millions of these transistors across the wafer.
We're in front of a metrology tool here with a very cool looking wafer, and I see banks of litho equipment behind us. Tell us about that equipment.
Sure thing, Jim. These are what we call our 193 immersion scanners. 193 is the wavelength of light that we use in this current technology nodes that we run, and it helps us focus the resolution that we need. We use immersion or water to help us refract, which has a higher refractive index, to help us gather more energy and more information down onto the wafer. That's what we need for this technology node. What you see back here, some of these scanners range anywhere from $100 to $125 million in cost, and we have banks of these that are required to run this factory.
That's amazing. There's a lot of chatter about the next generation of lithography, EUV. What's EUV?
EUV, or extreme ultraviolet light, takes the technology node, or takes the wavelength down by a factor of 10, anywhere from 11 to 14 nanometers. That's the sort of wavelength we need as we start to go forward in our technology nodes, which Intel 5, 3, and beyond. These scanners were about 125 mil. EUV takes it up to about $250 million per scanner, and that's what we're going to have in a not too distant future.
Wow, very, very expensive. I imagine it requires a lot of smart people. Tell us about the people in litho.
We have engineers and technicians that work in litho, all with a very strong STEM background. The technicians typically have a 2-year STEM degree, and the engineers anywhere from a 4 to 6-year STEM degree. And the reason why we appreciate the STEM background is because we've got a lot of complex decision making and problem solving that we've got to do on our feet 24/7 to help sustain and run the factory.
That's a lot of brilliant talent, just like yourself.
Thanks,
All
Jim.
right, let's leave our audience with a fun fact. Why the yellow lights?
That's a great question, Jim. During the early developmental cycle, it was realized that the white light would actually interfere with the lithography process. It would denature the resist and impact the pattern. So through those troubleshooting process and the developmental cycles, yellow light was seen not to impact the resist and help us produce the pattern fidelity that we needed. And hence we stuck with yellow light ever since.
Very good. Thanks for talking to us today.
Anytime, Jim. Thank you.
Hi, we're here in Ocotillo's Remote Operations Center. This is the hub where the thousands of wafers that we run in the factory every single day are controlled across the thousands of tools. And I'm here with one of the managers, John. Good to see you.
Good to see you too, Jim.
So thousands of wafers across thousands of tools. How many tools does an individual run in this fab?
Well, we have 50 technicians per shift that monitor and observe 4,000 tools across the 4 different factories that we have here. They monitor each and every wafer that runs through all of the tools, and they can monitor all of that progress through here in this room.
That's amazing. I imagine to be able to run that much volume of product requires a lot of automation. What kind of automation do we use for that?
Our automation systems are always evolving and improving upon the lessons that we learn with each technology. And currently, our automation system handles about over 4 million calculations to determine where the whip can move and the best way to get that through the factory.
That's wonderful. The people that run this have to be super smart then. What kind of skills do you require in here?
A lot of them have degrees. Everyone has degrees from various backgrounds, and they help contribute to the problem solving that we encounter on a daily basis. 98% of our product runs automatically through the factory, but it's that 2% that really causes the need for these highly skilled technicians at every station that we have. They troubleshoot and critically think through the different problems that these lots have, and they find the solution and drive that to getting that wafer out the factory.
That's wonderful. All right. So with all this automation, I imagine security is an issue. How do we keep things safe?
Good question. We have a lot of firewalls in place, very tight connection here in the rock. We're in a closed environment. In fact, some of our equipment is hardwired into the factory due to the sensitivity of the connection to the tool that they have. And so we limit the outside influences that way. And then even within the room, we have limited access to the different tools that each person runs so that only that person has access to that tool.
Very good. Thank you, John.
Thank you.
There's my home OTF.
Yeah, very spacious, actually. Very nicely organized, yes.
Yeah. Anything else that you can think about from an industry perspective, Paolo, from what you saw to today?
First of all, I like the dress code of the technicians. It's very casual, and it's Arizona. So I remember when I used to come to Arizona, I used to have ski gloves because I couldn't drive afterwards. The steering wheel was so hot that I couldn't touch it. But anyway, indeed, the cost of lithography has gone up, but on the other hand, 125 million against 250 beats the 125 now. So I'm glad that you caught on to it, and we'll discuss some more when we get to the video. So finally we're coming into the mainstream, it's good that Pat came back and gave the wake-up call. Okay, let's get on the latest. Okay, and the fact that you can run everything primarily, with 50 techs, looking at the double screens and so forth, it really pays for all the sensors that we always requested the suppliers to put in place, and all the communication system. Finally the computer can keep up with that. And so I remember the time when we had hundreds of people running with carts, loaded with wafers in this way, bouncing into each other. But, I always could get my runs out first because I would take them out for coffee, and that was a good bribe. My run were flying through the fab always. I don't think you can do this with the computer nowadays. You have nothing to bribe it with. So anything else you want to add, James?
The only other thing I would say is, so the fab that we're running today, it runs Intel 7 technology, it runs 14 nanometer, we run 22 nanometer. So we run all those technologies. And so this is a good setup because those technologies use immersion lithography. And Intel 3 and 4 and 20A and 18A, we're going to use a new technology called EUV, which we kind of reference in there. So this next video is about the future in EUV. So roll that one, please.
Good introduction.
In the 21 years I've been reporting at Intel, I've seen amazing products and the machines that help create them. But the machine I'm about to show you blows my mind. Come with me behind this door and I'll show you. This is it, an EUV, or extreme ultraviolet lithography system. It is likely the most complicated machine humans have ever built. It pushes Moore's law forward, and chip makers cannot produce leading-edge chips without it. But more on that in a moment. The EUV machine is a reality after 35 years of sustained research and development from lithography leader ASML, Intel, TSMC, Samsung, and others. Delivering just one of these tools to Fab D1X in Oregon took 3 747 cargo planes, 40 freight containers, and 20 trucks. The school bus-sized machine comprises 100,000 parts and weighs nearly 200 tons. So what exactly does this EUV machine do? Intel co-founder Gordon Moore observed that the number of transistors crammed onto a processor doubles roughly every 2 years, a cadence that has continued for more than 50 years and has long been known as Moore's law. The more transistors and components on chips, the cheaper and more powerful they become. Chip manufacturers use lithography machines to project circuit patterns onto silicon wafers. For decades, they have kept shortening the wavelengths of light on lithography machines to print features for ever smaller transistors. In pursuit of Moore's law, Intel engineers have produced inventions such as high-K metal gate technology, tri-gate 3D transistors, and strained silicon. Intel and other chip makers have also adopted processes such as double and quad patterning and water immersion lithography to get the most out of today's 193 nanometer wavelength light. But to make transistors even tinier, the industry needs lithography machines that use radically shorter wavelengths. This EUV machine produces light at 13.5 nanometers. Compared to today's machines, that wavelength is more than 10 times smaller. So how does this machine work? Put on your best thinking caps and I will try to explain it simply. First, extreme ultraviolet light does not exist naturally on Earth, so we have to generate it. Because this tool is so large, it needs 3 floors in the fab. Its laser, about 15 times more powerful than ones used to cut steel, sits on the level below the clean room. A beam transport transmits the laser pulse up a floor into the EUV machine, where a generator fires tiny droplets of metal tin, each droplet only about 1/3 the diameter of a human hair. And that powerful laser, flashing at 50,000 times a second, hits the molten tin. The metal vaporizes into a plasma. This plasma releases light in the extreme ultraviolet range. A collector mirror gathers the 13.5 nanometer EUV light and shoots it to a scanner, where it pinballs off extremely precise mirrors that shape the light into slits that create patterns of transistors and interconnects onto a silicon wafer. See, wasn't that simple? Just a couple more remarkable facts. Newer factories at Intel have ceilings 16 feet high. They are raised to 25 feet where these EUV tools rest, because it takes an overhead crane system to assemble the heavy system components. How precise are the EUV machine's optics? Here's the math. It's analogous to an astronaut standing on the moon with a laser pointer targeting the tip of my fingertip here on Earth. ASML is already working on an improved version of the EUV tool that will offer even finer resolution lithography. Intel is currently the first customer in line to receive one of these next-generation machines to prepare for the Angstrom era of computing. Isn't this mind-boggling? Hope you enjoyed coming behind this door to see this marvel of engineering and a tribute to human ingenuity. Thanks for watching. I'm Rob Kelton.
With that, that's our series of videos to show you the fabs. So.
Okay, so you opened the door, so I need to tell you how this technology came about. It came by accident. Actually, we could have lost it very easily. In 1995, Jerry Parker had a meeting with Mitsubishi. He walks out of the meeting and he shows me a sketch. There was a circular fab. He said, they're going to put the synchrotron in the middle of the fab with all these spokes and so forth. What are we going to do? So I said, okay, let me go find out, first of all, if it's true. So I went to IBM to find out, to Mitsubishi. These were the proposers of the synchrotron approach and so forth. And then at the end, we concluded that the probability was small because it took multiple masks just to make a good mask. X-ray is not very strong, actually, despite what you may think. So you put your pattern for the mask on like a plastic paper, and then you have to mount it. So they had all different kind of shift in the pattern and so forth. But they could, in principle, after 8 or 9 attempts, to make a good mask. Now, in the mid-90s, the major element of the Intel strategy was to make the gate small. You make the gates smaller, you get a higher frequency. But with optical lithography, it wasn't easy. But fortunately, the sales guy said, binning, we can sell different frequencies because we couldn't really get the right number, okay? So when I came back, I say, Jerry, there is one probability. One mask would pay for it because you could make the gate much smaller. And he said, well, suppose, ideal case, I have to sit at this poker table. So there was Scalpel also that was producing shaped E-beam, IBM. Do we have anything? And I said, well, you have Star Wars. What do you mean you have Star Wars? Remember President Reagan did all these beams and so forth. But then in 1989, after the Berlin Wall collapsed, the national labs were told, make some money of all this stuff that we research, and we never made anything out of it. And so they had developed one of these techniques that was called soft X-rays, because X-ray is 1 nanometer. As you saw in this picture, ultraviolet is 400 nanometer, and this is 13.5. So anybody would know that this is closer to X-ray and so forth. But X-ray would have meant a knowledge that X-ray was a good technology, even if it was soft X-rays. The press doesn't know the difference, right? So we had to invent something, and we invented this EUV, extreme ultraviolet, okay? So I was trying to think, how do I explain to a normal person how ridiculous this is, okay? So suppose you go to Elon Musk, he likes to do rockets. And so the guy from NASA said, you owe us money because, we invented the rocket. Say, oh, no, this is not rocket. Look at this video. See, it's gliding in this way. This is a EGV. What do you mean is an EGV? It's an extremely gliding vehicle, right? And if you can think you can explain this to somebody and make them believe, well, EUV is in the same category. And so, since this was going to be, a trading item, we kept it alive in '96. But then in some point, the national labs in March of 1996, they said, we're going to shut it down. And so decision point came. And so by August 1996, we had to write a check for 40 million. And it was difficult to convince Grove because he was completely against R&D. Because Palo Alto, where I work, and Fairchild could never transfer anything to Mountain View that was 10 miles. So when he and Gordon started Intel, say, write it on silicon, don't write it on paper, don't publish anything, and so forth. But we had a way of selling it. This was supplier development. This is going to be useful in the future. So we invited the 3 US suppliers, 2 Japanese, and SML. And we explained that this, I've done the back of the envelope calculation. By then, I have been working for 10 years with Nikon. And I say, nothing is going to be ready until 2010. And so by 2001, when we developed the first prototype, everybody dropped out except SML. And Martin van der Brink was the guy that really held the place because his own lawyers advised him against signing because the patents belonged to the national lab. So you had to deal with the US government, and you had to deal with a lot of problems, and everybody told him no. But these are the key moments in history where he said, I don't care, I'm gonna try anyway. So by 2006, he produced the first prototype, 2 prototypes. One went into the black hole, that is IBM, so nobody could see it. But the other one went to EMEC, because the distance between EMEC and Veldhoven is about an hour drive. So everything that SML does, almost everything, they put a prototype in EMEC. And so I was a member of EMEC at that time. So what we used to do, we would fly the wafers from Oregon with the Intel masks. Then we have bought a separate time on this machine. We would do the expose. And in case in 2010, indeed, the machine was available, we developed the alignment marks and all the other stuff. And in 2010, indeed, I got saved by the, December 2010, the first machine got delivered to Samsung. But the power was only 20 or 30 watts. And we calculated you need at least 200 watts to get a reasonable throughput. And so very, very reluctantly, finally, by 2012, SML realized that they had to buy Cymer. That was the guy that was making the sorts. And then it took in the next 5 years to put it in place. But by 2017, they delivered to our sister companies, Samsung and TSMC, 11 machines. That was the magic moment in which the machine was beginning to tweak. At that time, Intel was distracted by other things, and so didn't pay as much attention. And so now 120 machines have been delivered in the field. So I'm looking forward to Intel boosting up the number of delivery, but I know that is a challenging job. So good luck, James.
Yes, you bet. I talked to my fab manager friend in Ireland about it basically makes the dock completely busy for a whole week just to deliver the machines, as you saw in the video. So
oh yeah, it's a gigantic, but what is very creative, that essentially SML is an assembler at best. All the mirrors and stuff are made by Zeiss, the source. So they have been very creative, as opposed to the Japanese company or the US company that wanted to build everything ground up. They really have designed these parts like a Lego, so that you can send them on 747, and you see they are gigantic, you need the cranes, and they have all these gears they have to hook up, but they hook up for real, okay? So that the engineering, the machine really has been their key point, because the Japanese companies or the US company would build, like an artisan, each machine tricking and so forth. That's not the case for SML. So they deserve the success, because nobody in his right mind except Martin van den Brink would have put money on this technology, collecting now after 20 years finally out of this. But if Parker hadn't walked out telling me, look, they're gonna have X-rays, when they would have called us in March of 1996, I said, we discontinue the program. I say, oh, go ahead, But the thing that is funny, I say, since this was going to be a trading item, after in 2001, when eventually the prototype was built, IBM called us and said, would you like to have a cross-licensing agreement? And you know what we said? No, thank you. So we had, it's one of those cases, there is so much more. Of course, this, in the technology, you're playing chess, right? And this was a chess move to scare IBM, to keep everybody believing that Intel was going to do great. And people got so excited. They even say, a slogan, on the floor by 2004. Now, this was absolutely insane, because it was impossible for a machine to be on the floor by 2004. But the whole industry began publishing, making masks, making resist. And so we created this tsunami that after eventually in 2017 came to fruition, okay? So it's one of those cases we could have lost the technology very easily. But since only the paranoid survived, okay?
Well, hey, let me ask Jim a quick question then. Jim, how has the role of a fab operator evolved over the last 50 years? And Paolo can probably even speak further back.
Yeah, actually, I started Intel as an operator myself, working in the burn-in ovens of unloading and unloading the devices so that they get electrically and thermally stressed. But if I talk about the fab piece of this, and Mike here can remember, our technicians and operators used to manually load and unload the wafers onto the machines. And we didn't have all the AMHS, automated material handling systems, available to us. But now it weighs too much, and we have the automation which can direct it. And so it's quite evolved. And so they spend more time. We have the rock folks that run the operations, but our technicians today really maintain and repair the equipment. And they got to keep it up 90% or higher of the time, because the machines need to make money. So our technicians are really skilled at the equipment work.
So since you talk about automation, let me tell you another story, okay? So all the fab managers were concentrated on yields, anything that can decrease the number of defects and so forth. So in 1996, I initiated an effort that was called I300i, a coalition of 13 companies to go through the 300 millimeter transition with the least amount of money, because Intel failed the 150, IBM failed the 200, millimeter transition. And by 1994, everybody voted to be number 2. Nobody wanted to be number 1. So the only way of doing it, we managed to have this coalition with 3 companies from Korea, 3 from Europe, 6 from the US, and TSMC. And so the goal was really jointly to develop specs for the equipment, a unified spec, so that the supplier will go build it without us building each one of us prototypes and wasting a lot of money. But a giant opportunity came. I had tried to introduce automation since '91, but it was very difficult because all the fab managers say no value added, wasting my time. And so what happened, finally, the health and safety said that the cassettes of 300 millimeter are so heavy that the operator cannot lift them. So you have to develop a system. So the early system was a cart with a crane. You automate the crane, you lift the cassette, it was really awkward. And so, I decided that was the precise time to insert automation. And so we began the discussion in the middle of 1996. And I went to SEMI, try to understand, how do we make it a standard? Say, we let everybody run for 2 years, then we take the top 2 or 3 options, and then we have a ballot. I said, no, this is not going to work. How do we make a standard now? Well, we have this strange clause. It's called provisional standards. You can put a standard now, but it has to be approved within 2 years. So within I300i, we discuss what we wanted, and the Smith were opening from the top. So you had to be opening from the side. Then there are pins and codes, right, so that the equipment can recognize them. And most of all the equipment has to be built for free, because it used to be $100K bonus if you want to automate a piece of equipment, right? It became the standard that the equipment had to be built in this way, okay? And then the Japanese wanted to have their own standard. So by 1997, I had become a karaoke superstar. And so I negotiated according to the Japanese procedure, and they agreed to the same standard that was called E15.1. And so with this, automation was approved. And now I had to convince the toughest people, the strongest people, the fab manager of Intel. And so this is a typical case. The way you run a company is with a democratic dictatorship. So all the fab manager voted against, but I got 2 votes, Splinter and Parker on my side, and 2 is larger than 10 under some conditions. And so we approved to go ahead with automation, and we did in a very skillful way, because in the transition, we did 130 nanometer. We did on 200 millimeter, only 10% on 300 millimeter, while we were familiarizing ourselves with the automation. And then by 90 nanometer was 100%, 300 millimeter fully automated. And since then, the fab manager could never live without it. And so in typical style, they said, we thought about it, but we couldn't explain it simply. And so that's how it came all about. And so I'm glad that now has become you can imagine you would have to have 10,000 people, right, to run all these wafers. In fact, I tell you, when I was hired a first child, my test was if in 2 days I could find the wafer, I was hired. Because they had cassettes everywhere, and so I said, what is my training? If you can find the wafers, this run in 2 days, then it means you got what it takes. So,
Hey,
so
let me
anyway.
this is James Cape. Let me break in for a minute and ask Jim something real quick. If all goes as planned, how will the capacity of the Ohio fabs compare to those of Arizona? And also, when is the Ohio go live without giving away anything that you shouldn't?
Yeah, no problem. So actually, first thing, the two fabs that we're going to build in Ohio will be sort of replicates of Fab 52 and 62. So my 27 and 37 will be about the same. Now it's a greenfield site, so there's some things that'll be a little bit different, but the capacity for Ohio will be equivalent to the 52, 62 in Arizona. And the timing for this one we've publicly announced is that we hope to be operational by the end of 2025. It takes a couple of years to get the construction done. It takes a little while to qualify all the equipment that's in there, and then you got to qualify the process. So that's why it's about 3 years out from now.
So James, I had another question actually. When we used to have the Intel U, there was no Intel University. When we transfer from development to manufacturing, the yields would do a U for a year. Okay, and that compelled us to do the copy exactly. That is not the most desirable technique because new equipment comes, new ideas come up that could actually improve manufacturing. So how observant is still Intel of the copy exactly methodology?
Yeah, copy exactly is still alive and well, although of course, like everything, it evolves. It is most important at technology transfer that the copy exactly exists. At that point in time, you want your equipment configuration to be the same, all your specs to be the same. Then when you hit a point like I'm at today, where it's evolved is now you have a lot of brilliant engineers who have great ideas, and you allow them an opportunity to be able to make the changes. From there, the change control, if you have multiple fabs that are on the same technology, we have these joint engineering teams that then they'll go, okay, your idea, it's working, you write a white paper, all right, we're all going to do it the same.
Okay, yeah, I remember that was actually something that we had introduced. It had to be accepted by all the fabs. It used to take a lot of time. Maybe by now we are more, skillful in how we do this. But at least there was an embryo of a methodology to do something. And you're right, the thing that really changed everything was the transfer to 9.1, in which the yields in 9.1 and the yields in D1 were precisely the same. After we had yelled at everybody because nobody wanted to do copy exactly, essentially I had to go to, you remember Ken Moyle was like 6'5", right? And explain you cannot order equipment anymore. Now you're gonna simply use what this flaky guy in development are using. But Tom Hartman imposed really this methodology. And then when Bob Baker received the technology and he had the same yield, then he and Youssef signed, we invent a copy exactly. And it really always let people invent whatever they think they have invented as long as they do it right. So I'm glad to know that everything is still functional. James Cape, do you have any?
Yeah, hey, Jim, there's a lot of questions here around, as you might suspect, a lot of questions around, hey, golly shucks, when's Intel going to catch up versus TSMC, to be very direct?
Yeah, let me see if I can answer this way. Pat coming back has been a breath of fresh air for our strategy and because he keeps talking about this thing called torrid pace. So, it's well documented in Intel's 10 nanometer technology, we fell behind. But what we have going on right now in just the next few years is Intel 3, Intel 4, 20A, 18A, and they're happening in parallel. So that, whatever the foundry decide to pick, they'll be able to do that one. So in the next 3 to 4 years, these technologies are supposed to come out. And I just read an article recently about TSMC's N2 node, which would be their 2 nanometer node, which would be equivalent to a 20A, right? If you start to get the nomenclature down. And I think we're going to be in a dogfight here in that 25, 26 timeframe for technology space. So Pat's got 3 things he's looking for this for IDM 2.0. 1, get the capacity in place, my job. 2, the technology development folks get those technologies delivered. And 3, make sure that we have products that are competitive on, at every single, whether it's a laptop, a server, or whatever else. And when we put all 3 of those things together, these next 5 years, I promise you, my Intel alumni friends, we have some real big opportunity to regain all of the luster that we've had in the past that you were all part of.
That's great, Jim. There's a lot of questions obviously around the TSMC, but one specifically that I thought was interesting is, what is Intel doing to meet TSMC's defect densities and usability for designers? Example is the 1275 has a track pattern, and it is difficult to design, as well as meeting the IR drop requirement. So obviously somebody who's been to fab, much smarter than I am, but what are your plans in that area?
Yeah, I do think that one of the things that maybe has evolved here, it's still under the same culture piece, right? We have this culture item called One Intel, but I think falling behind has given us an edge on that One Intel of, guys, we really need to work together. If we're going to catch up, the design features, the process characteristics, and then being able to make that manufacturable, we have to work together as a team. So I've seen improvement in that particular space, so that of our collaboration that exists. And I do think that starts to play out in this 24, 25 timeframe. Now, we're also still all competitive in our own different fields of, all right, I'm going to deliver my fab part, I'm going to deliver my process part, I'm going to deliver my my product part of that one. But I think it comes down to the Intel collaboration and improving in that particular space.
Yeah, on this subject, something that still needs to be articulated, right? Because if you go to TSMC, you can get 500 nanometer products. They're still 200 millimeter. In fact, they're adding capacity on 200 millimeter, larger than 45 nanometer, and so forth. And on the other hand, they are pushing the leading edge. And so the spectrum of foundry is gigantic. And I think what hasn't come across yet, Intel has to very strategically select a very specific sliver. You cannot expect to have the same kind of breadth. And so maybe it's too soon to ask you if you have any idea, but feel free to decline if you don't think it's appropriate, okay?
Yeah, it's a little early for me to talk about the foundry space. We have an executive Rendier who's leading that space, and it'll be a business unit, just like the server space or the client space. I know for me as a fab manager, it will bring new requirements, right? Whatever the end customer wants and their customization of that one. But I'm still not in the space yet that I really know what's going to be asked of me. So
the only thing I was listening as you were saying, the number of nodes that you're running in the same factory, is there anything 45 nanometer or above still running in Intel?
In New Mexico, yes.
Oh, the Fab 7, 11, they're still running some of that?
Yeah, I believe they still are running some of that technology.
Okay. But I think,
not 100% sure, but yeah.
Covering that space would be very challenging. So that's why it's not your job, but at some point, all of this needs to be clarified. Okay. Anyway, this was as far as the foundry discussion.
Jim, one other question we have here that I think is pretty interesting, given that we're coming out of COVID here, how are you addressing your supplier and hiring issues, particularly in the context of building out Ohio? That's got to be a significant challenge for the team.
Yeah, I do think, especially because we're centered here in Arizona and Ohio, what you called out is a huge challenge for us. It is the hiring and supply of talent that exists. A couple of weeks ago, we for the Ohio piece, as an example, we brought out all of the education leaders from Ohio State, Columbus State, all those folks, and said, hey, meet our Arizona State and our Maricopa County Community College leaders, because we really need all of you to collaborate and build programs that are going to be able to deliver the talent that we need. And I was privileged to be able to be in an event here where we had kicked off Intel's manufacturing quick start program, which is a partnership with Maricopa County Community College. It's a 2-week program where Intel, either former Intel employees or current Intel employees, teach folks skills of how to be in the fab. Now, to be low grade level, entry level positions, and it actually is pretty well targeted towards our, getting our technical females and other underrepresented population folks into the field. But it's those unique programs that we're trying to build so that we can get the talent that we need, because it is one of our top challenges that we're going to face to scale Arizona and to start up a fab in Ohio.
Yeah, I mean, if I think of a similar case, when in '92 we were compelled to open a factory in Ireland, and we imported 100 people from Ireland in D2 that spent a year because there was no knowledge of what a semiconductor is and so forth. And additionally, I don't know if you're going to have the same problem. We hire each single plumber and each single electrician that was in Ireland, and everybody hated us because they couldn't get the water leaks fixed, the light goes out. I don't know if how you're going to have all of these problems, not to the same extent, but compounded, because just building one of these monster 200,000 plus square foot factory, you're going to kill the real estate business, you're going to kill the plumber and so forth. So don't run for office there, okay? You won't be very popular.
Hey, Mike, can you add a little bit? You have some experience of starting up a new fab like this with
yes. So right? I was going to mention that when I was in, I got privileged going out to open up the Fab 68 program in Dalian in China, and one of my jobs while the fab was being built was going to the university, the technical schools, to measure what capabilities do they have versus what we needed, because in Dalian there was no semiconductor industry, so we weren't taking from recruiting from other companies. We found this massive gap, so we actually created a 13-week program that had English in there and then basic skills from vacuum, model-based problem solving and all that. And one of the challenges we ran into, we found out that many of the people we were hiring, we assumed, hey, rode bicycles and changed tires and all. We quickly realized, oh my gosh, a lot of these are from the middle class and they just paid to have that done. So we came up with a creator. We actually got bicycle stands from the United States and bought mountain bikes, and we had them all set up and taught people, this is a torque wrench and this is a combination wrench, and disassembling bikes and putting them together or learning how to read specs. So we had a 13-week program to go put that together. And basically the site manager said in 13 weeks, they should be able to do preventative maintenance right away. And we were successful in getting that done. And that's the same thing we're doing with the Quick Start program with community colleges. I'm working on that. And part of that is, again, model-based problem solving, vacuum basics and all those type of things, as well as getting people. So that's the great part about Intel, where we go into those communities, we make that assessment, and then make people capable winning and bring up their efficacy so that we can win and get in the work we're going to get done. Same thing we'll be doing as we go out to, we'll say, in Magdeburg, Germany, doing the same thing in Ohio, and having those partnerships with the local businesses and local colleges is how we get that done. So we have great practice in doing that, and it's fun and challenging.
Yeah, I mean, when we initiated the activity in Ireland, they wanted to create an industrial park. And so they were very specific, you have this corner, don't invade. And we started with the freeway. And by the time we reached the other freeway, said, do you have any more plants? So I think you have to really win the local environment that initially may be suspicious, and then you have to progressively take it on your side, and then eventually, the benefits that come from these gigantic plants, they're always felt by the people that live around it. So it's a first, the next year is going to be hard and freezing, but hopefully by the summer it'll be in better shape.
I think that's the one great thing about Intel. We as the alumni have done, we continue to do that, be great stewards in our communities and partner with our communities. I think I saw Renee was on, Levine's on here as well. So we continue to go do that and have those partnerships. In fact, we have some contingency, some folks coming from Ohio, and hey, we're connecting them with different the city of Chandler and all these different community partners. Again, showing them what we do, hearing those stories, and again, bringing up the things that we've done and learned. Again, be great partners and great stewards in our community. So that continues to go on.
Yeah,
Staying on the
I'm sorry, go ahead,
same
Bob.
subject for a moment, if I look at the number of people in the university, I interface with several universities, and the number of people that are still interested in science, to be honest, are mostly Chinese and Indians. The local want to be lawyers, so MBAs, and make a lot of money, in stocks. How is your recruiting program proceeding? Because there are fewer people that are inclined to go into hardware. They want to go into software. You can build out on nothing a company, and so the mentality has drastically changed. I was talking to one of the professors at Stanford that has worked in semiconductors all throughout his life. And I talked to his son and said, I don't want to do what my father does. He works like a dog, 12 hours a day, enough of that. And he went into a trade company, just to do something different. What do you see on this side of the equation, either you, Michael, or Jim?
In those leaders that we brought over, we actually brought in folks as well. Now, it won't help me in 2024 and 2025, but you have to, when you come into a new site like Ohio, you're going to build a presence there for a long time, and we have room to be able to add more than 2 fabs there. So it's the K through 12 people you want to reach at the very beginning to get them interested in STEM. So they were actually in the leadership group as well to say, hey, by the way, this is what we need out of you, is to get people interested in STEM. Then at the high school level, there's some trade things that you could do to get there, and then obviously off to the community college and to the university. So you start as early as you can, because we're going to be there for a long time.
Okay, but you're seeing your way through, even though it may take some time, but you have a path that you're going to follow in doing this.
Yep.
Okay. James, Cape, you wanted to say something?
Yeah, I have a question that keeps me up at night. And that question is the strategic importance of fab. Fab from a national security perspective. To what extent is that recognized inside of Intel? And if it's recognized inside of Intel, does it all have to be Intel fabs being built, or much like the car industry, is it okay that TSMC and Samsung build fabs in the U.S. and Intel won't get in the way of that?
It's a little combination of both. I would say that every Intel fab cares about the security of its data and its information. I think the rock video that we showed, one of the things we try to highlight is, it's a small room, it's closed off, you have to have a badge to get in, things like that. And the data is segregated so that, people can't get into the information that exists. So that's global everywhere. I do think by having fabs here in Arizona and in Ohio, there's another kind of round of, customers who want to make sure that they stay in the United States and have that security and not have to deal with the international piece of that one. It gives us an advantage to have that domestic footprint as well.
Yeah, that makes sense. I mean, even back in the day when Intel had a military unit, a business unit, before Andy shut it down, you didn't let foreign competitors come in and build NSA-oriented, semiconductors. But following up from that, there's a kind of an interesting environmental question. In terms of water usage in a fab, we imagined it's gone up over the years, but golly shucks, how much water, and is it orders of magnitude more than it was back in the 80s and the 90s?
We from the 80s and 90s reference point, we've come down. So water is an extremely important resource when in your process. Each device that you make is like taking a shower when you think about adding up all the water usage with that one. And then we want to make millions of these devices that exist. So it's an important resource. So a couple things from the 80s to the 90s is, one is the engineering around the recipes and the use of the water is one piece of that one, but it's necessary, it needs to be present. But the second thing then is, how do you make sure you reuse and reclaim that water? Now, we started back in the 90s to 1995 with the Ocotillo brine reduction facility, where they took the hardness out of that one, and now it's biggie size. So that one, while we have a partnership there, we have our own Intel water reclamation facility on site. It's several $100 million of capital investments, and we get to the point where really we're only losing like the evaporation that exists. Now, Intel's got as part of its RISE program, get to a net positive on the water. What we do there is we actually invest in other people's water projects to make sure and help them reduce their footprint, and then our overall footprint for Intel becomes net positive. So lots of changes to one, we do need it in the process. How do we then recycle it and reuse it so that it really, the only thing that we're losing is the evaporation? And then how do you get to a 100% net zero footprint by supporting some of the other projects that people might have?
So kind of as a follow-on, is Intel thinking of partnering with municipalities on the coast around building desalination plants?
I don't think domestically we have that. I want to say that there is a partnership in Israel with a desalination plant. But I kind of remember that one, so don't quote me completely, but I believe that Israel has done something like that.
Yeah, these have been popular, in those places, Abu Dhabi and this other one, because money is not the object, right? But water is the object. So they have built these plants that are very expensive, but they would make sense only if you're close to the ocean. I haven't seen any oceans around Ohio or Arizona, so it would be a little more difficult in those cases. But I wanted to come back to the subject that we touched for a moment, expanding manufacturing in the United States. First of all, I work with the CHIP Act for the last 2 years because I'm the chairman of the International Roadmap for Devices and Systems. So in all the meeting, they have a token neutral presentation that has say, this is the view of the industry. Of course, I swing it a little bit to Intel side, but very subtle, okay? But the point is, a productive environment creates more competition and more productivity. And the main problem that people are trying to address now is, now there is 10% of the manufacturing done in the United States, of which 50% is Intel. How do we take it to 20 or 30%? This is unrealistic. And in the next 5 years, Intel by itself can do all of this. And so the fact that Samsung and TSMC also are building factories here, it actually for the overall business is good, because if you look at the business of TSMC, 70% is in the United States. So for all practical purposes, exclusive the fact that the headquarters in Taiwan, it's almost an American company. And there are many technology that I don't think Intel, as I said, should get involved. 200 millimeter wafers, 45 and plus nanometer. Let the business be. It's much better if somebody else addresses it. And so, building somewhat an ecosystem that actually accelerates overall manufacturing in the United States, and there are multiple fabs from the 3 leaders in one place, would make the United States very unique, because at this point, geographically, Samsung is in Korea and TSMC is in Taiwan, but to have a concentration with Intel having 70% and the other two, let's say 15% or so, the manufacturing volume, it would make the United States much stronger. One of the key points that I address with you, James, is there is a prototyping center, okay, that is the equivalent of IMEC and Sematech put together, that have been lobbied to have in Arizona. And I'm still seeking your advice how to proceed, in this with you and your successor, because that would be the right way of accelerating the technology when you can have, in this moment, IMEC is 3 or 4 generations ahead of Intel or TSMC, having something of that kind just in the, TSMC is North Arizona, Intel Ocotillo is South, right? And you put it somewhere in between, right? So I talked to the people in your government in Arizona, and I put it in the middle of the Indian reservations. And no, you cannot put it there. But so I think a way of coexisting. Of course, Intel takes the lion's share. It's a good element, and any additional ideas how to lobby for the prototyping center in Arizona will be just great. Okay.
Yeah, of course, I was born here in Arizona. Arizona is where I did my whole career, so I would love Arizona. And I'll hook you up with the right folks in TD and in manufacturing so that we can have this important dialogue.
Thank you.
Yeah,
Okay.
guys, and we're beginning to run out of time here. There is one last question that I think someone, it's really would like to get answered. Are there any other specialized technologies besides ASML that Intel is really dependent on for building fabs?
Suppliers or technologies?
No, technologies, a la like ASML.
Yeah, I would say, and I don't think I could comment on specifically what they are, but each technology node, you'll start to look at process features. And if I go backward in time, the gate change that we did for high K metal gates was an example of the materials that you needed to make that technology successful. Prior to that was an epi changes that were needed there. So for sure, each technology node, there will be some new innovations that our TD counterparts will come up with that might have some unique material requirements, and we'll have to pull those in. So, but stay tuned and we'll see what they come up with.
Let me add to it. Okay, so I think the arsenal of equipment we have is very good. With atomic layer deposition, we can deposit anything we want. EUV is the last technology we ever need to define anything. All of these elements are pretty solid. What is not solid is the materials, because we find the new materials that have new application and so forth. And as you know, they come from everywhere in the world. I'll give you an example. When we introduced copper, the price of copper went up, even though we use, 1 millionth of the consumption of copper in the world. Okay, so one of the elements, we are not, a strong player if we really want to lobby for one of these elements, and we have to have somebody much bigger than we are in consumption to really protect, access to these materials. And you can see nickel now, all of a sudden, lithium are important. So the highest risk is the materials. And this, we don't have enough volume of this material. In this case, we use a minuscule amount that we need another industry to be interested in these materials to really have the situation. If you touch rare earths, these are China. Okay, so you have lithium, you can find Colombia, you can find some. But these are very strange. I'll give you an example where we were really creative. There was once upon a time something called soft error. That is, when we package parts, some of the lead contain some radioactive material. So Intel had to go all the way to find a mine in Alaska, someplace, in which we could dig this special lead. They have very low radioactivity, but it was only open in the summer because everything would freeze in winter. And so this was the first encounter with some strange materials. This, I think, will happen. But I think the material side, the equipment side, is in reasonable good shape. At this point, Applied and LRC, SML with Zeiss, they're big enough that they can take care of almost anything in my mind, okay?
Well, guys, we're almost, we're over time, but Mike, I think you had one last comment, and I'll need to wrap this up because we're beginning to lose folks.
Yeah, I think for the technology, I think the packaging, that's been amazing with, the EMIB and the Fovros and all that. So we talk about the fab side. I think the assembly test has done a tremendous work in seeing those, having our partners that are down the street from us where they do most of the development work. So not just the fabs, but the assembly test process has been amazing. And those partners are really helping us out as a corporation for innovation as well.
let me
That's
add
great.
something to it. So you may say that Intel, fell behind in the process technology, but it didn't in the packaging technology. Intel and TSMC are in the same par precisely on packaging. So in the fact that Ponte Vecchio and all these other can be assembled is because this technology exists in the United States, but only Intel has it. And TSMC has it because it's simply D2 relocated to Taiwan. When we shut down in 2008, D2, all the Chinese engineer went to Taiwan. So the two technology are very sister technologies, okay? But in this respect, Intel is absolutely on the leading edge, and the wafer size, James, go faster, has to catch up, but in packaging, there is no contest. It's not the Vietnam style that Michael had to do, but it's a much more. And the other thing is this doesn't need to go overseas because it would take impossible training, impossible equipment. So we actually, on the leading edge, we solve the packaging problem. It never needs to go anywhere in the United States. So that is not an issue. We need to take care of the wafer size. And so that's what we are doing. And our junior team is going to announce at 2:00. So we want to make sure that we cheer him up. And with the earnings, Pat is going to come out with some revelation. Intel 2.2, who knows, what it's going to say. So, it's very creative. So, may come with something that we haven't even anticipated in our questions or in the answer, most of all.
Yeah, so hey, let me wrap it up real quick. Jim, I'm sure you probably got an earnings call to get to. And I would say many thanks to today's attendees, panelists, and the Intel Alumni Network team. And also a real special shout out to our esteemed Mike Trainer, who is a board member and an events producer extraordinaire. In the coming weeks, there will be a link to intelalumni.org that captures this video event once Mike gets post-event editing done. And please remember, we got two really cool events coming up in May. We got the grid modernization event moderated by board member Jeep Klein in conversation with Lisa Lambert of the National Grid. She was at ICAP for many years and worked in product marketing. And then we will also have our Bum for Alums hosted by Intel VP Jerry Batista. What's cool about this is going to be the first opportunity to meet people in person in either Santa Clara, Oregon, or Arizona, as well as online. And I just want to thank everybody. This was great. Paolo, marvelous. Thank you. A great level of detail. Jim and Mike, go get them. Trust that all of us alums are rooting for you guys. And remember, your Intel alumni can help you. A lot of us are still working. We're still at the grindstone. So come bug us if you need some help. Thanks, guys.
If you're bored, come call me.
Yeah, come
Yeah.
on.
Hey, we will.
We got
Thank you,
openings.
James. Thank you, Michael.
Hey, bye,
James,
guys.
Thank you guys,
James.
everybody.
Thank you, guys.